Determining the maximum and minimum values of quadratic functions. The output of the quadratic function, meaning the y-coordinate of the vertex, is the maximum or minimum value of the function, depending upon the orientation of the parabola. We can see the maximum and minimum values as in figure 9. So let's take a look at the vertex of this parabola. First, we can see that it's opening upward, and the vertex is located at 2, 1. Now, the reason why it's opening upward is that if we look at the coefficient in front of here where I have highlighted, that means that it's a positive value. That's why it's opening up. And if it's opening up, that means it goes down to the minimum value here. So the minimum value is the y-coordinate of 1, and it occurs at when x is equal to 2. Now, on the one to the right, we can see that the vertex is negative 3, 4, and this parabola is opening downward. And the reason why it's opening downward is because this part right here is negative. So therefore, if you're thinking about like a roller coaster, when you're going up the roller coaster, it meets its maximum and then goes back down. So the maximum value is the y-coordinate of 4, and it occurs at when x is equal to negative 3. So it's really important to distinguish between those two. Now, there are many real-world scenarios that involve finding the maximum or minimum value of a quadratic function, such as applications involving area and revenue. So for example 5, we're finding the maximum value of a quadratic function. Now, a backyard farmer wants to enclose a rectangular space for a new garden within her fenced backyard. She has purchased 80 feet of wire fencing to enclose 3 sides, and she will use a section of the backyard fence as the 4th side. In part A, we want to find a formula for the area enclosed by the fence if the sides of the fencing perpendicular to the existing fence have a length of L. So let's use a diagram such as we can see in figure 10 to record the given information. It is also helpful to introduce a temporary variable W to represent the width of the garden and the length of the fence section parallel to the backyard fence. In this figure, okay, this is the garden. And what do we know? We know that we have a length here and we have a length here. So we have 2 lengths. So we know we have 2 L's. Okay? Now, we also know that we have 1 width because we're not fencing this part. So we have 1 W. Okay? And we know that we have a total of 80 feet of fence. So that means that we have only 80 feet of fence available. So that means the formula would be length here plus the width here plus the length, which is equal to 80. Or we can simplify this a little further. Since we have 2 L's, we can say this is 2 times the length plus the width, which is equal to 80. So this allows us to represent the width W in terms of L. So if we write our formula 2L plus W equals 80, we can solve for W by subtracting 2L from both sides. So now we know that W is equal to 80 minus 2L. Now the reason why we do that is because of the following. Okay, in step number 3, now we are ready to write an equation for the area the fence encloses. So we need to know the formula for the area of a rectangle, and that is the length multiplied by its width. So we know that area is equal to length times its width. So we're keeping the L out here, but recall that we replaced W to be 80 minus 2L. So now what we have is L in our entire right side of this equation for the area. So we're going to distribute the L to get A, which is equal to 80L minus 2L squared. And then we want to write this in terms of a function. Because L is the input, we're going to say A of L is equal to 80L minus 2L squared. So now in part 4, this formula represents the area of the fence in terms of the variable length L. So the function written in general form is A of L which is equal to negative 2L squared plus 80L. So what we've done is we figured out what the formula is. Now what we want to do is we want to figure out what dimensions should she make her garden to maximize the enclosed area. Now, step number 1, the quadratic has a negative leading coefficient, which is negative 2. So we know the graph will open downward, and the vertex will be the maximum value for the area. In finding the vertex, we must be careful because the equation is not written in standard polynomial form with decreasing powers. This is why we rewrote the function in general form above. Since a is the coefficient of the squared term, we know that a represents negative 2. We know the value of b represents 80, and we don't have a value of c, which means that c is equal to 0. And now what we're going to do is we're going to find the vertex. So we know the formula h is equal to negative b over 2a. Plug in the value of b to be 80, plug in the value of a to be negative 2. We get a positive 80 over 4 and reduce that so that h is equal to 20. Now we're going to plug in 20 into the function above to find the value of k, or the output. So a of 20 means we're plugging in h to be 20. So we have negative 2 times 20 squared, so it's negative 2 times 400 plus 80 times 20. Well, negative 2 times 400 is negative 800. 80 times 20 is 1600. When we add them together, we get 800. So now we know that k is equal to 800. So the vertex is going to be 20 and then 800. Well, remember that this represents the maximum. So since that is the maximum, then the maximum value of the function is an area of 800 square feet, which occurs when the length is equal to 20. When the shorter sides are 20 feet, there is 40 feet of fencing left for the longer side. To maximize the area, she should enclose the garden so that the two shorter sides have length 20 feet and the longer side parallel to the existing fence has a length of 40 feet. Now this problem could also be solved by graphing the quadratic function. We can see the area where the maximum occurs on the graph of the quadratic function. So this is the maximum at 800.